Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Composite Materials from the paper Functional Materials. So let us start with the purpose of this module, which is made to make the students familiar with it. First, the class of materials called composites. Second, we will discuss the various possible constituents of composites and their forms. Third, the elastic properties of composites are discussed. Fourth, the mechanical properties of composites are discussed. Lastly, the commercially and technologically relevant composites are discussed. So let us start with a basic introduction about the module. There are already several classes of materials available. These are metals, ceramics, polymers, etc. Then why is there a need for a still other class of the materials like composites? There are two main reasons for this which are interconnected. First, modern technologies, they demand materials with multifunctional characteristics. Second, the demand for the materials with properties significantly better than the existing ones. Currently, materials, they have their own limitations, and hence there is a need for combining the good properties of one class of materials with that of the other. For example, cements. Metals, they have decent strength and ductility, and they have good roughness. However, the density is on the higher side. Ceramics, they are relatively lesser dense and are very good temperature resistant. However, they are beset by poor roughness. Plastics, they have low density, very good ductility. However, they lack thermal stability, chemical resistance, and have a very poor mechanical properties. Temperature capability of various materials. So students, this figure gives a glimpse into one of the properties, which is temperature capability of current materials and what was expected in future. Even a cursory glance of this figure tells us that not much was expected from regular class of materials, but from a different class of materials known as composites. So now we will discuss what are composites. Now let us discuss what is a composite. In simple words, it can be described as non-homogeneous mixture of other types of engineering materials, that is matrix and second phase. So this figure which is shown in this slide gives a better understanding of what is really meant by a composite. As shown in this figure, composites are nothing but a mixture of any of the two materials. Usually, one of these would form the base or the matrix, and the second material is present in the form of dispersoid or fibers. So, based on the definition of composites, we can broadly classify them into three classes, or basically four types of classes we will be discussing over here. First is metal matrix composites, where the primary phase is a metal and the reinforcing phase can be metal, ceramic, or polymer. Second is ceramic matrix composites. Ceramic is the matrix phase and it is also the reinforcing phase in most of these composites. Ceramic matrix composites with metal or polymer reinforcement are not common. Third is the polymer matrix composites. Here, the polymer forms the matrix phase and it is reinforced by various kinds of metals, ceramics, and even polymers. Fourth kind of composites are carbon-carbon composites, where they use carbon fibers in graphite matrix. They are used in nose of the wings, brake plates of airplanes. They have a very high temperature resistance and wear resistance. They also have low impact toughness. Intermetallic composites. Intermetallics, they are a class of materials which is formed when two or more metals they form a compound. These intermetallics they are usually found in alloys at different compositions and hence together these can be viewed as a composite which is very useful for high temperature structural applications. They are lighter, stronger, and more temperature resistant alloys, so they can be used for aerospace, automotive, and chemical industries. They are suitable for temperature above 1200 degrees Celsius. The examples of intermetallic composites are TiPe12, TiAl, Nb3Al, and nickel aluminium. Functionalities of intermetallics. Now students, till now we have discussed what are intermetallic composites. Now let us discuss about the functionalities or the properties of intermetallic composites. Intermetallics, they have a very high melting point and retain good mechanical properties at these elevated temperatures. They possess good functional properties like resistance to environmental degradation and chemical stability. Now, the intermetallics have lot of advantages. These are low plasticity, very high strength, very high wear resistance, increasing strength with increasing temperature. They are or they possess low toughness and low ductility, however, much like ceramics. However, when they are present as a part of composite alloy, these deleterious effects are counterbalanced by the matrix phase. Intermetallic composites. So intermetallics, they can form two kinds of composites. First, the metal matrix intermetallic composites, where the matrix is made up of the softer metal or alloy and the hard phase consists of intermetallics. Best example is the nickel superalloy demand for the material systems which can withstand long-term exposure to elevated temperatures has led to the development of intermetallic matrix composites IMCs. Conventional composites. In the conventional sense, composites consist of two phases, a primary phase and a secondary phase. Primary phase forms the matrix phase or a base, and secondary phase is embedded inside it. So students, as discussed earlier, it can be classified into three categories, which is metal matrix, ceramic matrix, and polymer matrix composites. Now, if the secondary phase is a metal that is reinforced when the primary phase is a metal, then powder metal parts infiltrated with a second metal. And if the primary phase is a polymer, the examples are plastic molding compounds, steel belted radial tires. If the secondary phase is a ceramic and consisting of the primary phase as a metal, then we can form somites, fiber reinforced metals. And if the primary phase is a ceramic again, then we can form silicon carbide whisker reinforced Al2O3. And if the primary phase is a matrix, then primary phase or the matrix is a polymer, then we can have plastic molding compounds, fiberglass reinforced plastic. Now, students, if the secondary phase is a polymer consisting of metal as a primary phase, then we can have powder metal parts impregnated with the polymer. And if the polymer is a matrix or the primary phase, then plastic molding compounds or Kevlar reinforced epoxy. So there are various roles of by various phases. That is, the two different phases, the primary and the secondary phase, they have very specific roles to play. Role of matrix and reinforcing phase. First, let us discuss the role of matrix phase. Matrix material is expected to first provide the bulk form of the component, second, hold and protect the reinforcing phase, third, share the load with the reinforcing phase, and lastly is to deform partly so that the load can be effectively transferred to the reinforcing phase. Now, reinforcing phase is expected to first provide the reinforcement by carrying the bulk of applied stress, and second is to bond well with the matrix so that strains are continuous. Now students, let us discuss the each category of composite in detail. Here we will be discussing when the matrix material is a metal, that is metal matrix composites. Metals are known for their very high ductility and strength. However, they have relatively high density. Hence, the primary purpose of metal matrix composites is to enhance the specific strength or specific modulus, for example, by adding lightweight fibers, or to improve its high temperature properties or wear properties, for example, by adding ceramics as the second phase. It must be emphasized that amongst the composite metal matrix composites are the most commonly used material systems. Ceramics and fly ash composites are very well known and widely used metal matrix composites. Ceramic matrix composites, or we can say when the matrix is a ceramic. The primary purpose of the matrix phase is to provide form and support to the secondary phase. Ceramics and glasses, they are not known for their toughness and ductility, and hence the ceramic based composites are very rare. Since these materials are very good insulators and have very high chemical and thermal stability, ceramic matrix composites finds use mainly in high temperature applications. For example, thermal barrier coatings on aerospace or rocket panels. It has been discussed earlier that ceramic matrix composites are usually reinforced by different ceramics. The purpose of such reinforcement is to improve toughness and reduce brittleness. Polymer matrix composites. Polymers have ultra high ductility and are mainly lacking in strength and high temperature properties. As far as strength is concerned, polymer matrix composites can be reinforced by strong fibers to give it the requisite strength. Fiber reinforced polymers, FRPs, are a very good example of this, which are not finding applications in automobile plane panels. Polymer matrix composites, however, are limited in their applicability for high temperature applications. Since polymers have very low density, hence the addition of secondary phase for the purpose of light weighting is not a consideration here. Carbon-carbon composites. Apart from the above three classes of composites, there is still another class of composite which does not fall in any of the above categories, and this is carbon-carbon composites. Carbon is a very unique material that exists in different forms, from a very soft graphite phase to a very hard diamond phase to a very strong carbon nanotubes. Hence, different forms of carbon can form the matrix as well as the secondary reinforcing phase, giving rise to unique properties. Such composites have very good strength as well as high temperature and mechanical properties, and hence they have found applications in nose and brake plates of airplanes. So, students, let us discuss now the reinforcing phase. Reinforcing phase can again be of any of the above type of materials, including carbon and boron. The reinforcing phase can exist in various forms. First, fibers, long strands with circular cross sections, and the diameters ranges from few microns to fractions of mm. Second are the particles, particulate shaped, again ranging from few microns to a fraction of mm. Third are the flakes, two-dimensional particles like platelets. Fourth, infiltrated phase, when the secondary phase acts like a filter in the matrix. They are usually found in PM. Next, we will discuss now the reinforcing phase, that is fibers. Fibers, they are usually tubular or rectangular, or they are hexagonal in cross section. The fibers, they can bear the major share of the load. Filaments structure of fibers, they are mostly defect free and hence they have a very high strength. They can be continuous or discontinuous. Whiskers, they are also the form of discontinuous fibers with the diameter as small as 1 micron. The fiber orientation, it is a very important parameter in determining the overall strength of the composite. Now students, we will discuss the reinforcing phase, that is fibers. This graph shows the variation of tensile strength versus the fiber diameter, and the below figure shows the various orientations of the fibers, that is, these are basically the possible orientations of fibers. Another important aspect is the bonding between the fiber and the matrix. Hence, the fiber orientation and the bonding between the fiber and the matrix are the important parameters in determining the overall strength of the composite. So, if the two are not bonded properly, then the fibers cannot take the load as expected. Now, still we are continuing the discussion over the reinforcing phase, that is fibers. Various materials are used as fibers. One of the most important characteristic that is expected from these materials is that they should have a very high strength. So, there are some of the common materials and their properties are which are used as fibers are as follows. First is the glass. Glass fibers are very strong materials and they have a range of modulus. Second is carbon. As stated earlier, carbon is a versatile material and it can also be used as fibers in the form of nanotubes or whiskers. Third is a boron. It has very high elastic modulus and is used in aerospace applications. Fourth material are the ceramics. Silicon carbide and aluminium oxide are very commonly used fiber materials which have high strength, high modulus, and are low cost as well. Fifth, obviously, are the metals. Metal whiskers can also be used as fibers. This table shows the typical properties of fiber materials used as reinforcement in the composites. So here the diameter, tensile strength, and the elastic modulus have been tabulated for different fiber material. The reinforcing phase, that is particles. Particulates of metals and ceramics can also be used as reinforcing phases. Even though they are very small in size, they are found to share the load and even improve other properties like wear and high temperature stability. Cermets, ceramic particles in metals, is one of the best example for particle phase reinforcing phase or the particle based reinforcing phase. Cermets are heavily used in tools and dies because of their excellent wear resistance and high temperature. High temperature strength. So, the distribution of particles is random and homogeneous, leading to isotropic properties of the composite. In case of fiber-based reinforcement, the distribution is always preferred in a certain direction, leading to anisotropic properties of the composite. Strengthening in particle-based reinforcement is not much dependent on the geometry, as all the particles can be considered to have an aspect ratio of 1. However, it does depends on particle size. Based on the particle size, strengthening mechanism can be put in two classes. First, small particles causes strengthening by dispersion hardening and improving the load carrying capacity of matrix. Second, larger particles share the load with the matrix and proper bonding is very important. Now let us discuss another reinforcing phase, that is flake. Flakes are basically two-dimension platelet-like particles. Examples include the silicates of potassium and aluminium. These flakes are usually applied as reinforcing agent in polymers. They add strength and stiffness to polymers. Platelet sizes ranges from 0.01 to 1 mm and thickness is usually of the order of 1 to 5 microns. Now let us discuss another reinforcing phase, that is infiltrated phase. When the matrix phase has a porous structure, the reinforcing phase can be infiltrated into this porous structure. In these cases, second phase acts like a filler that covers the open pores. Reinforcing phase fills up these pores and thus provides additional strength and integrity to the structure. Some of the metal matrix composites are manufactured in this manner, where the metal foam is created first and then the second phase is infiltrated into this foam. Conversely, molten metals can be impregnated into parts formed by powder metallurgy, thereby reinforcing the overall part. Oil impregnated bearings and gears can also be considered as the examples of this type of reinforcing phase. So students, let us summarize what we have learned in this module. First, the temperature capability of various materials is being discussed. Second, different types of composites are discussed. Third, intermetallic composites, that is, their properties and their advantages are discussed. The comparison of various conventional composites and their categories are discussed. Next is the role of matrix and reinforcing phase, and based on the choice of phase classification is discussed. Next, the metal matrix, ceramic matrix, polymer matrix, carbon-carbon composites, these types of composites are discussed. Reinforcing phases like fibers, particles, flakes, infiltrated filters or phases, they are discussed in this module. Thank you.